but the math is... Should I repeat or doesn't it matter?
Sorry, I forgot to click record. I think you can keep going.
Okay. So as I was saying, it would be very nice at some point to port it to Lim4. Nonetheless, the math is always the same, so I'm going to give you like an overview of both the math and formalization part of this project. So the title of this is Formalization of Class Numbers, Computation, and Mulder Equations. And let me start with the motivation for all of this, which is the second object mentioned in this title. So a topic of great interest for all number theorists is the Diophantine problems. So what's a Diophantine equation for those of you who are in different areas? It's essentially a polynomial equation for which we want to find integer solution. Let me give an example that everybody will know. Pythagoras theorem. Pythagoras theorem says that the sum of the squares on the sides of a right triangle is equal to the square on the hypotenuse. And it is well known that there are infinitely many solutions to an equation like this, so infinitely many right triangles with integer sides and hypotenuse. For example, 3, 4, 5 is one such triple, but there are infinitely many of them. On the other hand, some of the people here are very fond of this second example. If we replace the exponent 2 by n when n is at least 3, there are no integer solutions except for the trivial ones, that is, the ones for which this one of the unknowns is still. This is Fermat's last theorem. So the Diophantine problems can be very easily stated and not so easily proved. And the Diophantine problem that we focused on is a Mordell equation, which is an equation of this shape. So the unknowns are x and y, and the form is y squared is equal to x cubed plus t. This is some integer parameter. And these equations were first studied by Mordell in the more general setup of elliptic curves. Indeed, such an equation is the equation of a particular elliptic curve. And as such, it is known by Siegel's theorem that there are finitely many integer solutions, integer points. Of course, saying finitely many doesn't say any and doesn't say how many. So the interesting part is still to actually find what the solutions are. So there can be several different approaches for this, more or less elementary, but the one we followed and formalized is an approach that uses class group descent and aims at proving this particular specialization of this theorem, which holds for some d's. In particular, we take d a negative square-free integer, that is 2 or 3 mod 4. This is for simplicity because formalization can be hard. And we also assume a technical condition that will be clear for those who know what it means. For the others, let me just say that it is going to be a technicality that allows us to do things in the naive way, and it still works. So this technical condition is that 3 does not divide the class number of the ring Z to which we adjoin square root of d. Then this Mordell equation has solution if and only if this is of some particular shape, that is -3 times a square plus or minus 1. And in that case, we have an explicit shape for the solutions. For example, y is these two numbers here, and x can be found at this point by solving the equation in one unknown. So let me say just a few words about what's the sketch of the proof that we implemented. So it goes as follows. We start by a putative solution. The idea is to use descent, that is to say, let's assume that there is a solution, let's find the smaller one, and then either we find a contradiction or we find some conditions on the solutions. And what we would like to do is to factor. So we had y squared, if you take the d here, minus d is equal to a cube. So we would like to factor out and say y plus square root of d is times y minus square root of d is equal to x cubed. Now, if everything worked as for the integer numbers, we would say, okay, these two factors are coprime, the product is a cube, and then each of them must be a cube. And the technical condition that we had to assume allows us to do that. For those of you who are more into algebraic number theory, what we do is we take the ideals generated by y plus square root of d, y plus minus square root of d, and x cube, and we say, okay, I times j is equal to L. L is a cube, I, j are coprime ideals. We have this technical condition. We deduce that I is a cube of a principal ideal. And then we can write indeed that this generator, y plus square root of d, is equal to the cube of some element in this field, so a plus b square root of d, where a and b are integer numbers. And so doing the computation and comparing coefficients gives the claim. So that's the idea. And as you can see, there are a lot of things that one would like to have in order to also formalize this proof. In particular, we will need to have these rings here, to have ideals, to have class numbers, and to be able to carry out computations. So these are the objects needed. Some of them were already or partly in Matlab. Some of them we had to define. And in particular, we had to focus on these two final items here, bullet points here, explicit computations in quadratic rings and class number computations. So let's go step by step. First of all, and we just clarify the definitions just in case somebody is wondering what I'm talking about. So a number field is finite extension of the field of rational numbers, which means that you take a polynomial, a reducible polynomial, for example, x squared minus 2, which doesn't have any rational roots. And we say, okay, we want to consider some set where we can do addition, multiplication, inverses, and so on, where we don't just have rational numbers, but also the square root of 2. And the smallest set where we can do all these computations is called the field extension of q by square root of 2. That we can do with any irreducible polynomial, and the explicit elements of such a field will be given by this expression here. And in particular, we don't just want to focus on the field, but also the ring of integers, which is some sort of generalization of the integers inside the rationals. And so, for example, we would like to be able to say that square root of 2, 3 times square root of 2, and so on, is an integer, but 1/3 square root of 2 is not an integer. And the definition that allows us to do things nicely is this one. So all the elements that are roots of some monic polynomial with coefficients in Z. Okay, why all this fuss? Because rings of integers are what mathematicians called Dedekind domains, and what we care about is that we can do unique factorization, only not necessarily in the between elements, inside the elements of these rings, but we can do that for the ideals. So we can do something like what I wrote here. We can talk about products of ideals and say I times j is equal to L cube and so on. And we can consider a notion of prime ideals and do unique factorization exactly as we would do with integer numbers normally. And using this important result, we can structure some sort of descent algorithm that doesn't work in general with elements, but works with ideals. And the ingredients necessary for essentially the complicated step in the proof sketch are these two blocks here. One is this theorem due to Lagrange that says that if this number here, which we would like to be able to compute the class number of t, which essentially tells us how far an ideal is from being principal in a given ring, is coprime to a certain exponent n, then I to the n is principal if and only if I is principal. And then we are able to perform this descent, as I mentioned earlier. So the product of two coprime ideals is a nth power, then also the two coprime factors are nth powers, which is what we need. And is what we have to port to Lin. Now, as far as the explicit computations go, the rings we're interested in for solving our model equation are the fields of this form and the ring of integers of these fields. So if we adjoin just the square root of t to q, then the ring of integers has two different shapes depending on what the modulo 4 is. So for simplicity, we only focused in the theorem we formalized on the second case, so that we didn't have to deal with denominators. But at least technically, everything can be just adapted to make it work also when d is equal to 1 mod 4. And the goals were to define in Ling what this c squared root of d is, to be able to see it as inside of q squared root of d, and to prove it is a Dedekind domain in our case. In order to do that, we defined this structure, which we called quadratic ring, and it takes 3 inputs: R, which is our base ring in some sense, and then A and B, 2 elements in R. And in the structure, we have 2 elements, which are internal elements of R. So what does it mean? We would like this quadring to be the extension of R by the one root of a certain polynomial. A and B will be the coefficients of the polynomial. So more specifically, we are extending R, adjoining one root of the polynomial x squared minus ax minus b. So R could be z, and A could be 0 and B could be D, and we would be adjoining the square root of D to our ring Z. And then B1 and B2 would be the coefficients of our element with respect to the basis 1 alpha. So in our case, 1 square root of D. We proved everything we needed to prove in order to do our proofs, to do our job in Ling. So in particular, started by proving that it is a commutative ring, and then we also needed to have it as a Dedekind domain in order to use our properties about unique factorization and class numbers, etc. So in the case that D is 2 or 3 mod 4, we proved that the quadring that we needed are integral closure of q square root of d, as I mentioned earlier. So the rings of integers of q square root of d, and this automatically implies it's a Dedekind domain, and we can use everything that was already in MATLAB about that. And then the possibly more interesting part from a Ling point of view is to decide how to do the computation inside the quadratic rings. So I want to spend a few words on that. The first tactic that we defined is this calc-sac, which is very down to earth. So essentially, we just do an next to recall what the structure in the quadring is, and then we do a repetition of split. So that would be constructor now. Simple ring to do the computation, which works, but can be potentially very, very slow. A more intelligent way to do things, which unfortunately we implemented a bit later, so we didn't really use it, but it could be a good idea to have for the future, is this time-stable structure that is essentially a matrix that allows us to do the computation for the multiplication between elements of these rings, these quadratic rings. So you fix a reasonable basis, and you have your metrics that tell you how to put together 2 elements and multiply them. And then, of course, there's the really, really hard part that is going to the class number computations, which we needed in order to be able not only to prove our theorem, but also to prove the theorem that I showed earlier, but also to apply it to actually several instances of D. So if we want the class number of a given ring not to be divisible by 3, we need, for example, to compute the class number and check it is not a multiple of 3. So in order to implement the class number computations, we started with some previous work by Anand Sander, but also Narayan and Nuccio, about the finiteness of the class number. So the class group is actually finite, is a theorem that was already formalized in Ling before we started our work. And then we essentially tried to formalize some upper, lower, and lower bounds that allowed us to go on with the computation. And for example, these 5 are instances of lemmos that we have in our code, where class number is not only not divisible by 3, but is actually very small, either 1 or 2. So we can go on and compute the solution of the Mortal equations for these examples of D. So as far as the upper bound goes, we started from this theorem that essentially says that if we live inside a class group, which is a group formed by classes of ideals modulo principal ideals, we can always find some element that divides a somewhat bounded ideal, and that can be used to compute an upper bound on the class number. And this is quite general theorem. The difficult part can be to find this set M that gives bound. And on the other hand, for the lower bounds, we find something explicit and quite useful. For example, we managed to prove that under certain hypotheses, 2 is a lower bound for the class number of z square root of d. In particular, this happens when d is less than -2, which is in the first 3 cases of these examples here. And then after working on all of this, we were able to actually formalize the theorem that I mentioned and sketched at the beginning of the talk. So if we have a negative integer t, that is 2 or 3 mod 4, square free, and obviously not a square. And if additionally we have that 3 does not divide the class number of the corresponding field or ring, depending on how we want to state it, then this equation here, if it has a solution, then it exists some m such that y and d are of the form that I mentioned in the other statement. Probably it's more readable in LaTeX than in Lean. And in particular, we applied it in specific cases, for example, the ones that I mentioned, talking about the class number computation. So for example, in the last 2 lines that you see here, so for d is equal to -5 and -6, it can be proven that there are no solutions to the Mortal equation, while for the other 3 examples that I printed, one can find the solutions, and in this case, the only solutions have y is equal to 0. But in this other case, there are 2 solutions that are one the opposite of the other. So thanks. This is everything I want to say. Our link code is on GitHub, and as I said at the beginning, would be very nice to port it to link for at some point. Thank you.
Thank you very much. Are there any questions? Oh, now I've got to figure out where did that window go? Oh, there it is. Oh, Patrick has his hand up. Go, Patrick.
Hi, so thanks. That was a very nice talk. What was going on in the last or on one of the last slides with the D prime and the algebra map? I mean, the inclusion of Z into Q. Why isn't it simply the coercion? So what's going on?
Here, yes. So we had some trouble with the coercion and everything. So we had to, among all the things that we proved, actually show that there is some algebra map from C square root of D to Q square root of D. And D prime is actually D, but we ended up giving it 2 different names for simplicity. I don't know. This is, again, another thing that once we review for the Lean4, maybe we will come up with a better way to formalize it. I agree that it is a little bit weird.
But at least in the final statement, I guess you could restate it using only the D and Z, and I mean,
You mean without using
you without using
D
D prime.
prime
I
and this
understand that in
fact?
intermediate lemma it's probably useful, but when you state the final theorem, I don't see what would be the difficulty in stating the thing.
Well, I mean, mostly the problem is that, for example, in this theorem here, with the class number in Q instead of, of the field instead of the ring.
Yeah, sure. Well, anyway.
And yeah, I agree with you that the nicest thing to do would be to say just, look, D and D prime are the same thing, only in two different rings. So, but I remember that we had some problems with that, although I don't remember exactly what the problems were.
Okay. Thanks.
Thanks for the question anyway.
So
Same here.
if 3 does divide the class number, do you know an explicit counterexample?
I haven't prepared it. But again, even if 3 divides the class number, you cannot use this approach, right?
Right.
I can't come up with the example on the top of my head, but I believe that with
a
lot more effort we can see where it goes. Like
this sounds like a very feasible computational question.
Yeah,
right?
it does.
You find a D for which 3 does divide the class number, and then you simply brute force look for an example.
Exactly.
I just think it would be a very natural thing, because it might be very easy to do. Just
Probably,
simply find. Yes. Yeah, and that's why I'm asking. Because you could find it using Python or Paris or something. And
yeah, indeed. Actually, now that you mention it,
yeah.
Now that you mention it, Alex Best, who is in the audience, I guess, was working on making some sort of bridge between Lean and Sage in order for Lean to be able to call Sage for doing actually the computations and then get back the results inside Lean.
I don't know what, for this particular question, I don't know what kind of Sage. I can quite believe that Sage can say, "Oh, I found all the solutions to this cubic equation," but I don't know if it will give you a certificate.
Yeah, that's possibly a problem.
Because then Lean has to check it.
Yes.
Anyway, Eric has his hand up. Eric, go for it.
Also a question about computation. Great talk, by the way. On a previous slide, you have this times table structure, which uses a basis. When you say computation, do you mean it in the actual real program sense of the word that computes a number, or do you mean it in more of a Lean sense of helping you do arithmetic?
Oh, I mean in Lean.
Okay, because I asked because I know that basis is not computable. So sadly, while this looks like it ought to give you an executable program for computing things, it does not at the moment. And I was wondering if you ran into that. Okay,
yeah,
thanks.
I guess for your particular case, the basis is highly computable, because in fact, it's probably precisely what you're using to do the computations.
Exactly. So it seems a shame to then not be able to use this to actually do the computation.
Did you have
getting?
Go ahead, Patrick.
Did you try to do something like setting up a norm-num extension, or because that would be the kind of thing to try, right? Extending the norm-num tactic to handle those quadratic rings.
The honest answer to your question is I don't remember if we tried. Probably yes.
Did you have a problem identifying your concrete Z root D with the abstract number field Q, the integers of the abstract number field Q root D?
Yes, which is basically why we went through all the fuss of defining these algebra maps and everything.
Yeah, because somehow this thing comes up again and again. Mathematicians are very good at identifying structures. I'm quite happy to think about the integers of Q root D in 10 different ways, depending on what I'm doing, whereas Lean is rather less happy. I could sort of imagine that would be a pain point.
Yeah. Oh, I see in the chat that somebody tried to put the link, but it doesn't work. Let me try
Someone
to
in
find
the
it
chat,
again.
what's going on? The chat shouldn't be usable. What's happening?
She means Zulip.
Oh, I see. Yeah, people are talking about you in Zulip.
Let me see if I can find the link again. Just a sec. What is it? Oh, on archive. So on the archive version of this paper, in the abstract, we put also the link to GitHub. And I thought it worked, but let me check. Yes, it works. I don't know why it's not working, but where can I post it? In Zulip, is it better?
Oh, definitely better Zulip. Yeah, we're sticking to Zulip chat. Anyway, but we only have 3 minutes left, and Mark,
Okay.
Mark has a question. Go ahead, Mark.
Yeah.
Thanks. Hi, Nirvana. Thanks for the talk. It was great. I just saw that I just Googled Mordell equation, and I found that this paper of this note of Pete Clark, and he mentions the equation y squared equals x cubed minus 26, and it gives some solutions that don't satisfy the hypothesis.
The class number.
Yeah, and in that case, cube root minus 26 has class number 6, so that would be a counterexample of what Kevin was asking. So it's already, I didn't do the computation, but apparently Pete Clark did it.
Yeah, it's a very natural question.
Yeah,
because the technique clearly doesn't work.
Yeah,
then,
apparently it has other. I see now below it has other examples. X cubed minus 53 doesn't work either. So on. Yeah. X cubed minus 109 and so on. It has at least 3 examples there. This is a note of Pete Clark. Yeah.
It's too late to add these examples to the paper though, because this is I like the idea of Lean Together having kind of snuck in ahead of CPP next week. Who is speaking at CPP on the work?
Actually, we presented it last year.
Oh, of course, it's 2024. Yeah. Yeah, I'm 1 year out of date. Yeah, sorry, my mistake.